So I'm Gareth Jones, postdoc from the University of Cambridge. And today I'm pretty excited to be able to tell you about our work in the ALPINE collaboration, looking at kinematics of galaxies within the first gigayear of the universe. So my author list here is a little bit small, but really the ALPINE collaboration is pretty huge. This is a list of all of the co-authors and authors on the current set of papers. And we're currently spanning 11 countries. So I just want to point out that all this work is due to everyone's work. So you've already heard from Yoshi yesterday and Yana and Seiji today, but just to reiterate, ALPINE is an ALMA Large Program looking at 118 star-forming main sequence galaxies between redshift 4 and 6, looking at C2 and rest frame far infrared continuum emission. And there's a whole bunch of science that we can do since these are in the cosmos in the good south field. But we're just going to focus on the kinematics of the C2 for now. So C2 kinematics can include a whole host of different physical properties and processes. Seiji's already gone over the spatial evidence for outflows. Michele Genofi looked at the spectral stacking of C2 profiles and found evidence for outflows in the spectra. We can also look at mergers as something that's related to kinematics. Michele also looked at a double merger that shows evidence for a very large diffuse halo surrounding it, where I looked at a triple merger at redshift 4.6. But mainly what I'm going to focus on today is rotation and dispersion, where this is just an example of velocity field and velocity dispersion field. But I also want to point out that Mirko Despois-Sabatsky looked at dynamical masses, compared them to gas masses. So first I'm going to look at the work done in the survey description paper by Olivier, where we tried to do a morpho-kinematic classification. So Seiji showed this figure before, but just to kind of describe it in more detail, a group of 8 of us looked at a set of diagnostic plots, tried to classify each galaxy into one of 5 classes. And these diagnostic plots contain C2 channel maps, the wideband photometry in different bands. And then along the bottom here, we have moment 0 integrated intensity plots with continuum overlays and velocity fields, position velocity diagrams along the major and minor axes, and spectra. So by looking at these diagnostic plots for all of our galaxies, we tried to classify them as a rotator, which is a single galaxy with a nice ordered velocity field, a merger, where there's multiple components, or a single component with a really messed up velocity field. Dispersion-dominated, where we have a definite source with no evident velocity evolution, either extended and resolved, or compact and unresolved, or just too weak to tell. So the first cut that we did was we took our 118 galaxies that we observed, and Matthew Retherman ran a line search algorithm that found that only 75 of these galaxies were detected at more than 3.5 sigma in C2 emission. So we did this analysis for those 75. We found a really nice kinematic diversity, but we found that 12 of these galaxies were too weak to classify, mostly because these lines were very broad and we didn't have enough signal to noise in each channel to do kinematic analysis. So if we remove these 12, we're left with 63 galaxies. We find that roughly half of them are mergers, a quarter are extended resolved dispersion dominated, and the remaining quarter are pretty evenly split between rotators and compact unresolved dispersion dominated. So again, these are for galaxies between redshift 4 and 6. So this sort of kinematic diversity, where it's not all mergers and it's not all well-ordered rotators, is kind of nice. You might be surprised that there's any rotators at all around redshift 5, but the fact is that we see rotators pretty much anywhere we look. So of course, local galaxies, we have amazing observations in very high numbers. So this is an example from the Wisdom survey, where the resolving beam is to the lower left. We resolve the disk. It's definitely a well-ordered rotator. At intermediate redshifts, the KMOS 3D and the XIN CC-SINF surveys found evidence for a whole bunch of rotating disks using H alpha. And if we move out to higher redshifts, all the way up to redshift 8.3, we find evidence for rotating galaxies, mainly from the detection of a well-ordered velocity gradient. So yeah, ALPINE is 4.4 to 5.9. So finding disks in this redshift range is not ludicrous. So what we tried to do next was to analyze the rotation of these galaxies by fitting tilted ring models. So this is a mosaic done by Michele Ginolfi of the 75 galaxies that were detected in C2. And so we took each of these data cubes and ran them through the search algorithm at 3D Barolo to see which sources had strong enough emission to actually fit with models. And of these 75, we found that 26 were actually strong enough. And these are ordered in decreasing signal to noise. So we detect the strongest signal to noise and one low signal to noise source that happens to be merging with a strong serendipitous source. So yeah, this is the moment 0 or the integrated intensity. If we look at the velocity field at the moment 1, we see really nice kinematic diversity, some well-ordered rotators, some really complex mergers, and then some just obvious noise, essentially. Since these are data cubes, we can also look at the velocity dispersion maps, where again, we see some central velocity dispersion peaks, some peaks on the side. So yeah, in order to quantify this, we then fit each data cube with a tilted ring model. So we took the entire data cube and fit it with a model, which is much better than just taking the velocity field and fitting it with a model, because we can look at the data, the model, and the residual in multiple ways. So the first way is we can look at the integrated intensity, or the moment 0, for the data cube, the model cube, and the difference between the two, the residual. We can do the same for the velocity field, the velocity dispersion field, the position velocity diagram, which is a slice through the cube taken along the major axis here and the minor axis, where the contours are the model and the color is the data. And then we can also look at the spectra for the data, model, and residual. And this is actually the example shown by Seiji in a couple talks ago. And so you can see that evidence for an outflow there. So this sort of shows that we can see how well 3D Barolo is fitting these really simple ring models to each data cube. And we can also see where it deviates, because we don't expect these galaxies to all be perfectly flat, thin, rotating disks. We expect them to be surrounded by mergers and gaseous filaments at these redshifts based on comparisons to simulations. So in addition to looking at single galaxies, we can try and add on more evidence to the kinematic classifications that were done in the paper by Olivier. So we can say that some galaxies are very well fit by these tilted ring models with small residuals and very well fit spectra, pretty much perfect position velocity diagram fits. Some are fit with very low velocity gradients, but very high velocity dispersions. So these are dispersion dominated for sure. And then there are some galaxies that are just terribly fit with a tilted ring model because they are not rotating disks, they're actually mergers. So we can add on this evidence to the initial qualitative analysis. And a paper by Michael Romano and Paulo Casada will be coming out in the next few months looking at this sort of analysis in a more case-by-case basis. So I'd just like to point out that there are now 15 papers out in the ALPINE collaboration covering a whole bunch of different science cases. And if you're strapped for time and only want to read 3, I want to point you to Lefebvre, Betherman, and Feist, just looking at the 3 survey overview papers. But if you're interested in mergers, dust attenuation, IRX beta, luminosity functions, there are a lot of really interesting science cases. So just to conclude here, ALPINE is a really exciting kinematic playground, essentially. From the kinematic classification, we find a really nice diversity of sources. From an initial 3D Barolo model fitting, we see some are good rotators, some are good mergers, some are just dispersion dominated. But there's still a lot of work to be done. And then finally, with the rest of my ALPINE collaborators, I'd like to remember Olivier Lefebvre and his dedication to this project, and I'd like to dedicate this talk to him. So thank you.
Thank you, Gareth. All right, please post questions if you have any. I actually have one. So as you push this to higher and higher redshift, it's more difficult to distinguish between rotators and say mergers, because you don't really always resolve things, especially in imaging. So how well do you think you can do that at your highest redshift end, and what kind of resolution do you need to push this to even higher redshift?
It's a good question and a pretty large concern right now. Yeah, so these are only around 6 kiloparsec per beam. And so what we're finding is that we don't have the resolution to actually tell these rotators and mergers apart, even if they're only a few kiloparsecs separated. And so we don't have, there's definitely no chance of getting close separation mergers. But we do have high resolution 0.1 or 0.2 arcsecond observations coming up soon. So hopefully that should be good enough. But yeah, that's definitely a problem, and yeah, higher resolutions needed.
And do you think high resolution is going to be sufficient? I mean, are you still going to be able to detect those objects? Because obviously with high resolution, you get the fluxes are harder to detect, right?
Right. So yeah, these are all main sequence, and I guess one of the best comparisons is this work by Marcel Neilman. This is a 0.2 arcsecond observation of a main sequence galaxy, and I think they were able to detect it. It did take a long time from what I remember, though. This is ALMA C2, so yeah, instead of 30 minutes, it's going to take 10 hours per source, but it is possible.